Okay, so I'm kindly asking everyone to mute your cell phone here and welcome Kristian and Hewraz presenting the authoring design. And if you have a question, please raise your hand. I'll hand over the microphone because otherwise the live streaming audience will not hear your questions. Thank you.
Can I start? Okay. Hi, everyone. Welcome to this presentation. My name is Hewraz, and I work at Cisco in the NSO business unit in a team we call the architect support team. And my job is basically what the team name says. I provide architect support to our users and customers. And throughout the years of doing this, I've been asked the same question over and over again. How do I design my services in a good way? Well, today I have Kristian here with me to be able to answer that question. Kristian Larsson, he has an incredible amount of experience when it comes to network automation using NSO. He has been doing so for a while now at Deutsche Telekom. And he also used to work at Cisco. And back when he did that, me and him have been sitting down together, working on things where we have actually applied the things that he have experienced and learned from his time at Deutsche Telekom. And that is what we're going to try to talk about today, answering all of these questions about service design. Yeah, so most of the things and the concepts that we're going to bring up today actually comes from his real life experiences at Deutsche Telekom. But service design, it's a pretty broad topic, and there are a lot of aspects to consider when it comes to that. I mean, me and Kristian, we have been talking about this like for hours and hours, and we can go on for days with you guys, but we don't have that amount of time. So we have been splitting this up into two different sessions. We have one today and then one tomorrow, same time, same location. And we're gonna try to go through as many aspects of this as possible throughout this time. But the agenda is not really fixed, so if you have any questions, please, we encourage you to ask them. We want to give you the opportunity to actually tailor the content to fit your situations. So if you have those, just go ahead. Otherwise, we'll just go through as many things as possible, as much as time allows us. So what is service design? Well, as in any other software system, you need to be able to zoom out and to have a broader picture of the whole thing. You need to have architects or system designers that do so. And NSO is not different from that, right? You need to have someone who has this bigger picture, who does the rough shaping of the whole thing. And I think this here kind of, this is an interesting study that was published like 50 years ago or something by George A. Miller, where he claims that we as humans, we can only keep around 7 things in our head at the same time, plus minus 2. So that is about as much as our brains can handle. So how do we deal with life with only being able to have 7 things in our head at the same time? How do we deal with complex things like, I don't know, building a spaceship, right? We've managed to do that. That takes more than 7 things to have in your head at the same time. Or building automation systems. I mean, even the smallest automation systems require more than 7 things in your head at the same time. So what do we do about this? Well, we take the problems and we sort of chop them down into smaller, manageable pieces, right? Divide and conquer, the oldest trick in the book. And that is what we're trying to apply here as well. So we want to be able to find the right abstractions for these larger, complex pieces for us to be able to deal with them better. Because if we can do that, if we can find the right abstractions for our intent, then we can start to focusing on the bigger problems rather than trying to like fit the small pieces together on a large network of small pieces. If you've worked with any software engineering or development, or even NSO, you've heard about abstractions, right? That's not a new topic. We didn't invent it. But you've probably also heard that NSO services is a great tool for you to be able to create an abstract representation of your network and your device configurations. But we can go even further than that. We can create an abstraction of our abstractions using services and even scoping down or chopping it down the complexity even further. Let me show you what I mean here. So if you try to approach this abstractioning, we should keep a counter of how many times I say abstraction, because there's going to be plenty of that. Everyone takes a shot when I say abstraction. Um, you might address it like this. You have like 100 million lines of configurations in your network, and you want to create services to abstract them. So you create a layer of services on top of that. And then you want to create another layer of services on top of that as well, because someone said, hey, stacking services, that's a good way to do things. But then you will end up like this probably, or maybe. You will have 100 million lines of configurations represented by another 100 million lines of configuration on the layer above. And then a layer above that, you will also have everything represented with the same amount of configurations. That is a bad abstraction. I mean, that is not even an abstraction at all. The idea is that we want to be able to reduce the size of the configuration, or the size of data, to represent a larger size of data below. That is what we want to do. So then you say, okay, I might do it like this. I create, so this represents services. And then you say, okay, I create larger services that I put on top of my device configurations that will represent my network information. And then on top of that, you create even larger services to represent your services. And these larger services, they might deal with more, but the intent of these services, you just kept them the same. So it's still as big as the lines of configurations on the device. This is also not an abstraction. I mean, you've created bigger services, you have lesser services, but you haven't abstracted anything away. So how should you do it? Well, this is what we want to have. We want to have our 100 million lines represented by 20 million lines above that, and then a layer above that, we maybe even want to narrow it down to 2 million lines to represent the whole thing. But then you might say, aha, okay, so if I reduce this number of lines, will I lose data? How is this even possible? Well, no, you won't lose data, and it is possible, because you can actually remove things from your service intents that you expose northbound, such as, for instance, resources, integers, IP addresses, VLAN IDs, or things like that. This is information that doesn't necessarily need to come down from somewhere above. This can be derived from within NSO, because NSO has the knowledge that it needs. I mean, for when it comes to unique identifiers, you need them to be unique within the network. And NSO is aware of the network, so you can, from inside there, pick a unique identifier inside. It doesn't need to come from above. And when you strip that away as an input from your service intent, then you can reduce it dramatically. Like, you can remove 80 million lines of config just out of that. I mean, these numbers are made up, but you get the point. And furthermore, you can also have computed values, values that are derived from services that are already deployed, or other information that is already in your network, or in NSO, I mean. Let me show you what I mean. So if you were at Kristian's presentation just recently, you might recognize this picture. This here, what we're trying to show is that we have 4 routers managed by our NSO. And we have created IBGP neighbor services for those. And we want to deploy IBGP neighbors on our routers. On the right side, that will be our service intents, right? We will have 3 IBGP neighbors for each and every router, because we also want all of the routers to point at each other. So every single router has to have a neighbor for every other router. But if you look at this, the service intent, I mean, sure, it has been abstracted. The device configuration at the end is way more than this. So it has been reduced a lot. But just looking at it, it's quite a lot, right? And if we also would want to add a fifth router, right? Then we would have to, I mean, that task will also become a bit complex, because once we add that 5th router, we would need to add all of the other routers as neighbors to that 5th router. But we also need to go to every single router and add that 5th router as a neighbor to that router. That is a pretty annoying task to do, right? Even more when the number of routers increase. So do we really have to do all of this just to set up an IBGP full mesh? Well, no, we can actually create a service for our IBGP full mesh. And that is what we do. we create a service on top of our iBGP neighbor services that deals with all of this. So the intent of this one will only be the list of routers, and the rest of it will be taken care of. And we've been able to reduce so much of the intent by doing it like this. And then there are other ways of actually reducing the data or the representation from above. I mean, we have hard-coded values. Like, for instance, for your BGP sessions, you might want to have a hard-coded BGP timer. So you can just hard-code them into your service. You don't need to have that as an input or a choice from above. Or you can even reduce the choices even more. Like if you want to provide QoS services, you don't need to have your users given the full possibilities of configuring QoS exactly the way they wanted to and tweak all of the parameters. You can give them like 3 options. You can get a golden QoS version or a silver or a bronze one. And even there, that is also an example of how you can reduce the size of the input for our services. So this is how you should think about it until you meet this angry demon. What is this, Kristian?
Blah, 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 blah. Yeah?
Yeah.
Okay, excellent. Right. I don't know if you've seen this. Lord of the Things, right? We meet the Balrog of complexity. Some say he has the most things out of everyone and likes to build the most complex things out of it. And everyone knows you can't beat a Balrog at its own game. You can't win with a more complex solution. We must out-architect it with the right abstractions. So it's very important, I think, to remember that we must abstract. You have a clicker
there.
Oh, I have another one. Nice. So I've noticed this trend where loads of very detailed options are exposed all the way from very low-level services like RFS services up through our stack. And I think that the idea of this is that if everyone just exposes all parameters to the top, then we can have this central thing that sits on top that can orchestrate it all. And by doing so, we get a lot higher feature velocity, or so the reasoning goes, right? Now, if we just have this sort of pattern in our whole OSS or NMS stack, right, then we'll be able to put together product offerings much more rapidly because we only need to implement the changes in that top-level God orchestrator. And voila, we have a new product, right? I don't think that this works very well in practice. There are multiple reasons for this. But the first being that there is now overwhelming complexity. If you'd actually go inside of this box and think about, how do we sort of deal with this problem? Well, we would start by building smaller abstractions, and then we're sort of back to this. Why aren't we using the abstractions down here, right? So unless your network is run by Borg cube, we really don't want to do. We don't do well in exposing everything just up to the top. I think that the true goal behind this is feature velocity, right? Like we talked about. It's being able to assemble sort of and build new product offerings. We want to build new products quicker, right? But trying to achieve this by exposing all of these options to the top is really sort of a workaround, right? We have to ask ourselves, why is it slow in the first place to build new product offerings, right? And I think it's because we tend to build our network automation solutions out of many disparate systems, right? That they're tightly coupled together in various ways, but with a high impedance mismatch. So it's hard and it's slow to make changes. No single person has an overall view, but the logic is sort of broken down. It's actually, well, it's not like this, right? It's like the other solutions. So the overall problem is broken down and spread out in various different places, right? We get many people involved and many different teams need to be involved in order to get changes done. Instead, imagine, we do all of our network automation in NSO, like the sort of the deeper stacked service approach that we're advocating for, more or less, right? We use good, proper abstractions, and adding now some new product features. It consists of modifying these service layers, right? We probably need to modify the RFS to do new things on devices. We probably need something in between to sort of carry a bit of information through, and then probably expose something on the top, right? But this isn't particularly hard, right? A single developer can do all of this, probably in the span of hours. You couple it with a network engineer, and you sit down for a day or two, and you get changes done, right? Single Git repository, a single CI testing pipeline, and we can become very, very productive, very, very fast at this. But most automation stacks, they don't look like that. Instead, they are built out of these separate subsystems, right? So we need to modify our services down here in NSO. Then we have something on top. There's an adapter that now needs to see, oh, what's this new information, right? We have perhaps different sort of workflows associated with that, create, update, delete, right? Then most systems, they don't have model-driven northbound interfaces, so there's a new, well, not adapter, but a interface API, right? That probably needs to be explicitly modeled. Maybe you have inventory systems on the side or other sort of supportive systems where you do lookups or where you do resource allocations, and all of this you now need to update. And if you couple that with lots of different people spread out in different teams, these run on different sprints. I'm going to do it in the first sprint, or worse, this guy's going to do it in the worst sprint. And you're like, the dependencies get all muddled up, right? And then on top of that, you have release cycles. And they're like, well, we only release, every 6 months, and you just missed the window. So, haha, wait another 6 months. I think that these are more, we're sliding more into sort of organizational and process issues here. But I think it is important to recognize that the organization, it is reflected in the technology stack and vice versa, right? If we choose to build with many different systems, we are more likely to have an organization that matches those. You've probably heard of Conway's law, right? On the other hand, if we choose to build with simple, uniform solutions that tend to simplify the work, as well as the organization behind it, right? And the processes that we use to drive it. So we want to inspire building systems more like the one on the left here, right? Where we have a deeper stack of services in NSO that handles more logic. Not systems like on the right. This is my sort of stand-in place for something that's a script or a workflow looking, right? If you don't recognize the little swoopy-loopy logo. We want to concentrate and have our logic in a single place, but structured, right? And by staying inside of a single system, we avoid impedance mismatch. I say impedance mismatch, right? Because when we have different APIs and they are built on different ideas, then whenever you go between systems like this, you're going to find that impedance mismatch. Inside of NSO, writing configuration from one layer to the next is supernatural, right? The lower layer, like, add something in the Yang model, and then on top is like, you can immediately write to it, right? But if you have other systems that follow some different paradigm, this becomes much more troublesome. You have to work a lot, right? So single system, remove impedance mismatch, and by doing this, we get a simpler thing, and that means we have more time over to attack the essential complexity, right? So show that out there, right? But it's important to think of configuration inside the system flows down, right? Like this. There we go. So inside of the system, right, we're always internally consistent. But the devices that are external to us, that's really where sort of anything can happen, right? And I think that this is what we've done sort of throughout this is that we have a service design that reflects that, or I don't know, honors this. It takes it into account, right? I think that it's a very good idea to align your RFS services on devices. That is, a single RFS service should only write to a single device. You should not have an RFS service that writes to 2 devices or more, right? And we can see that here, right? Because these IBGP neighbors, 3 of them here, they all write to a single router. They don't write to anything else. So on the RFS layer, this is one of the sort of rules, let's say, that we have. And this is, again, because of this reality that we have, right? I'm supposed to be here. That things can happen down here. And when they do, if you run out of sync on a device, if you have to redeploy services, how do you react to that, right? Well, you want to like run redeploy on these services, or you want to do a sync from, right? And if they just touch a single device, it's super simple. We don't need to touch all those other devices, right? I think there's like the anti-examples here, right? Of I don't know, layer 3 VPN in the examples playbook probably. And it's like single service that writes endpoints to all the devices that are part of the VPN. You do this for a large service provider network, and you're like, oh, how many endpoints? 1,000, 10,000. You know, one thing is going to touch the entire network. So you're like, you know, out of sync on that device, and now, bam, redeploy of pretty much all services in the entire network. So it's just super inefficient. And that's why we want to do things like this. But it's also, I mean, we don't just create abstraction layers because it's fun. There's lots of them here, right? Just going to pick up my... I think we have to think about, you know, what is the problem that we're trying to solve at a particular layer. So we have sort of different focus, right? And this is one of the most important aspects of the RFS. We need to be able to react to things in the network. Typically something you don't think about like day one, you know, when you're sitting there writing your first service. But a couple of years in, and you're like, yeah, that would have been nice, right? When you're on the other layers, right? The CFS here, we need to think of what should people be able to order from us, right? So we should think in terms of, yeah, you know, data validation. They shouldn't be able to express things that are invalid. And then we have intermediate layers where we can sort of fill in and orient data after some other principle. So this is that whole reacting to events, right? That we talked about.
Yeah.
You talk about performance, right?
Performance, yes.
What we're doing here.
I'm actually gonna skip some slides here.
Oh. How are we on?
Exactly.
A little short on time. Okay. Yeah.
So I am skipping this.
Don't you, do you wanna... Det står här, ser du dina anteckningar?
Okay. Okay. Right. So you can actually gain throughput or gain performance by stacking your services. And I'm going to show you how. When I think about services, I think of them and I visualize them in this way, like a burger. And in this box, that is my service. It consists of an input, some logic, and an output. The input is the service intent. The logic is the create callback that you have written, and the output is the config. And then eventually it will push things down to the CDB or the devices, the device tree of the CDB. But that is how I view this stuff. So when you create a service, you do so by creating your intent. And typically, like just Kristian mentioned right now, you have services that are spanning over multiple devices. So your intent will contain a list of devices and some kind of intent associated to each and every device. That is what this here represents. So you create that intent, that will trigger the create callback of the service. And that will run some logic defined in the service package. And through that logic, this will generate a set of configurations. In this case, we have a set of configurations for device D1 and a set of configurations for device D2. And this part here, NSO has to process this data and it has to compute it. It has to generate a reverse out of these configurations because it has to be able to apply that once you delete your service or do fast mappy things, basically. So that is something that NSO has to do with this data. And it also has to compare it with the CDB to be able to know what kind of operations I need to do to apply this. Do I need to do create or delete or modify or so on and so on? So these two things can actually take quite some time the larger the set of configuration of your service get. And it increases with the size. So if you have a bunch of devices in your service and configuring a bunch of config for each and every one, this can take time. Nevertheless, let's continue this flow. So in this case, we computed, NSO computed, compared everything and saw that, okay, nothing is on our devices, so I'm gonna add this service configurations to the devices. And if we now want to modify this service, we make a modification to the intent. So you see that D changed from E, and it only affects device 2. the create callback will run, and it will run everything just as the service was created from scratch. So it will compute everything for D1 and everything for D2. And if you have more devices, it will compute things for that as well. And then we'll generate all the complete config set once again and do all of the calculations on it once again. Even the config for device 1 and even the config for device 2. And here it compares it with the CDB. It sees that, okay, this here requires a modification to this last parameter for us to be able to update it. So it makes that change and applies it to the device. But what I'm trying to say is here that there are a lot of computation that has to be done just for you to make a small little modification on this single device on one single place. So the performance on this can become really bad. And what do we do to solve this? Well, we stack our services. So here now we have a CFS representation of our service. The intent is the same. We have something representing one device and something representing another device. And when we create this CFS service, same thing, the create callback of the CFS service will run. And that create callback will generate a set of configurations. But this set of configuration is an abstract representation of the complete device configuration, right? This would be the intent for your RFS services. So it's a much smaller set of config compared to what is going down to the devices. And these two services will be created. The create callback of them will execute. A set of configurations will be generated, and those will be applied to device 1 and device 2. With a misspelled device there. But the nice part of this, or it is at the modification where the magic happens, because now when we modify our service, we make a modification on the intent that only would change the device 2. So we do that modification, CFS callback will run once again as if it was created, and then it will generate a new set of config where the intent for RFS device 1 is the same, but the intent for RFS device 2 has changed. So NSO does this computation, and then it sees that, okay, the only change that will happen is on the intent of RFS device 2. So that will change. And once that changes, the service callback is triggered. And only the callback for RFS device 2 is executed, not for device 1. And the new device configuration is generated through that and applied to device 2. And this is what we see here, that if we want to make a modification on a small part, then we don't want the whole thing to run again. We only want the one specific part of it to run. And this is what we achieve through this. And we're also hinting that, just as Kristian also mentioned, that on your RFS level, you want them to be per device, which is a natural way of stacking your services. And
yep, right-sizing services, yeah. So this is the next part. I mean, it's sort of the natural next step, right? I mean, sure, CFS, express what you actually want, and then RFS per device. But there's probably a little bit more information to go in with this, right? I think the single most important guiding principle is that of unit of deployment. So we want the service to map well to the unit that we deploy. But as we will see, this actually changes a little bit across these layers, is what I started talking about just a couple of minutes ago, right? And we're going to talk about the IBGP neighbor again. It's I think it's a good sized service, right? It models a single IBGP neighbor on a single device. That's the base, the RFS. And that's important because we want to be able to react to changes on the devices, right? It's natural that the RFS layer is oriented around what is natural on the device, so that when we go out of sync and those kinds of things happen, we can redeploy. Thus, the unit of deployment for RFS is really always per device, because we want to be able to take those kinds of actions, right? Right. There we go, blah, blah, blah. Same thing. And we naturally support multiple IBGP neighbor services on a router. which is then very naturally supported by having one iBGP neighbor service instance per configured BGP neighbor on the router. And I think this is also very good, right? Because the number of iBGP neighbors on a router is dynamic over the lifetime of the router. And just to put this in contrast, right? I mean, we could put iBGP neighbors as a form of like part of the base configuration on a router, right? Like we could say, well, maybe not for these devices. I don't know. They're probably core routers because they're part of full mesh. But if you have an edge router, it typically just has 2 connections, right? So you could say, oh, they always have 2 connections, no more, no less, and we'll put it as part of the base configuration, right? But I don't think that is natural. I think this is the better way. You'll actually find, at least when you do migration, like, oh, we started out with these 2 connections, but then later on in the lifetime of the device, we create another connection because we're migrating to faster 400 gig connections instead of 100 gig or something like this, right? So you want to be able to control at runtime when you're running your network, how many iBGP neighbors do I actually have, right? And for that reason, this is a very good size for an iBGP neighbor, right, on the CFS level. But these, individual BGP neighbors, they don't represent how we wish to interact with this when we deal with a full mesh, right? We already show that. You create a full mesh service. And here, we now orient ourselves around that, right? So what's the natural sort of level to express this? And I think, well, it's certainly not per device, right? But we want to think of the whole full mesh as one thing. And it's very nice to have a single service that sort of guarantees the consistency across the whole network for the service. And again, if you consider the layers that we have in the system, no one will come in and meddle here, right? Unless you gave admin privileges to the wrong guy and he's like, I'll remove stuff here, right? Like, you're not supposed to do that. You only change the input up here. So the rest is always internally consistent and guaranteed. And these are like really nice properties, right? We get that automatically computed. And I don't know, once again, like if something happens here, it's just here and down that we actually need to redeploy those RFS services, right? Let's see. There we go. So as I was getting to out there, right? I mean, a full mesh still isn't the way we really want to interact with this. I mean, should it be possible to add a router to the network and then forget to configure it as part of iBGP? No, we don't want that, right? And so on the CFS layer, we have yet another view where we orient it after what the user should be able to actually order from the network, right? We want to find the minimal set of things to configure and then use constraints on data constraints in order to enforce those kind of rules, right? So we want to make it impossible to express invalid network scenarios. So on the CFS layer in RESPnet, we have this list of routers, and if you set the role to core, it's automatically added into the full mesh, right? And I think that's a very sort of natural way of doing this, right? You pretty much, and then of course you can force that, oh, you got to pick a role for a device, right? And now you've made it impossible to express an invalid scenario in your network. So, and up here, the unit of deployment is typically a router, right? Or that's the service that we're looking at right here. And we're gonna get to the next thing. I can repeat the question otherwise.
You were talking about one device always, but we often do device pairing, primary backup things.
Mm-hmm.
Why not pairing?
You should do pairing, absolutely, for the services where it's relevant or where it makes sense. But that is what I think. You can do what you want. You don't have to listen to me, right? But what I think you should construct that thing on a higher level, right? So you can do on a CFS layer, you can talk about sort of redundancy pairs. This is the active, this is the backup. Super fine, right? But once you want to realize it down here, the thing that actually pushes configuration to the network, that's still an RFS service, and you do that per device. Because if your primary explodes and you're like there in the middle of the night and you just want to replace it, right? Which services do you want to rerun? You don't need to rerun these up here, right? We just want to rerun the RFS services to recompute whatever it needs to be recomputed, right? So anyway, here, the slightly more advanced, it maybe actually touches a little bit on on your question here. So first, let's just consider what it is we're trying to achieve, right? So down here, we have PE1, an edge router, provider edge. And all such routers, they're physically connected to two core routers. So I just made those things core routers, right? That's what the red lines are for. PE1 is not part of the full mesh, so instead it should be BGP route reflector client, and of course we should set up the physical connections. So if we start, lots of lines happening here, right? But this is the CFS configuration that we have for this. And I think this is quite beautiful, actually, right? It's super minimal. And I hope we have time for the demo, and then you'll see that it's not just stuff on a slide, it's actual reality. Okay, so if we start, there we go. Each router has its base configuration, right? So we add up the routers up here, ding, ding, ding. They all create some base config and all sorts of, I don't know what you want to add in there, logging, TACACs, things like this, right? That could be based on the role of the router, so some differences for core or edge, right? Then we define the physical links. So, well, just the red ones in this case, right? There are lots of other stuff in the network. We don't care about that. We only care about these two. So BB link, backbone link, I've shortened it here. We say we have a left side, router 1, that's that guy. Some interface, what do we pick? Gig 5, and then PE1, gig 0, right? So there's a left side and the right side, and there are two links like that, right? So that's the CFS intent. What does it look like? Well, we have CFS services up here. How do we sort of deconstruct that? Well, it becomes this, right? RFS per device. So we have a BB interface that just configures one side of it, right? That one goes on this router. You see that one, the other one down here to this router, and the same thing for that one, right down there and right down there. I think you can follow the arrows. We don't have the intermediate layer here. We just skip past that. We don't need it, right? You don't always need it. I think 2 layers. If you're going to start somewhere, 2 layers, CFS, RFS, probably makes sense just because of this. You always want to do per device RFS, but CFS, you want to express what you actually want to express. I mean, it doesn't make sense, I think. I mean, when we configure backbone links in the network, we want to order links. Links always have 2 sides. Why would you want to order one side? Then you can create an invalid network configuration, more or less, right? And then we also realized that for the P routers that are supposed to be BGP route reflector clients, that actually the IBGP topology here, it follows the physical links. So based on the same CFS, the links here, they're not just the physical links. We also reuse that for the IBGP configuration. So when now you consider our network, we don't need a single line of IBGP anything. It's encoded into the system, right? It's impossible to tell NSO to set up a invalid network, right? We enforce all of that with NSO. What do we have next? Yeah. Okay. So what we also do, hi, welcome. Sure, I think so. What we also do is we try to, I can show this in the CLI as well, but we try to structure all of our RFS services under each router, right? So this makes it easy to find them. So if we ever end up in these situations, we're like, oh, we don't want to redeploy them, we can find them in a single place, right? Is this? Oh, there it is. Oh, it's sort of animated. Okay. However, so you could do like this, but we drive most of these things automatically, right? So you don't actually have to run that. I'm just I'm just trying to demonstrate the structure that we use. Okay. What do I press on this? We're like 1 minute left. Is it the coffee break after this?
No.
No. No? Here we go. Thanks. Okay. So, lots of stuff here. Docker PS. Oh, that was not okay. Many lines. Maybe I can look at this. So this is RESPnet, the example Git repo that I've been talking about, right? So in here, I just thought I'd show. This is the container lab. So we have this topology, core routers, edge routers, some customers, and there's an NSO, and then they're connected in these various ways, right? And I just thought I'd show. So this is the NSO. There are no devices in here. And now we're going to add in what's it called? This one, right? Oh, it's an XML. There's a little make target. Oh, I forgot to show config net infra. It was empty before. You got to trust me on that. It was empty before. Let's see. I hope. Oof. Is this? Am I bitten by the demo devil? Let's see. Let's see in a second if it actually works. That's very busy. Stop talking. This is the show configuration net infra, right? So this is the configuration that I was just talking about, right? So here we define, we have our list of routers, role, core, 3 of them, role, edge, 3 of those, and then a bunch of backbone links, right? And I think this is pretty nice. I mean, this is super abstract, right? No IP addresses, no information like that, right? Just very, very sort of condensed and abstracted, right? I showed you there are no devices in here previously, right? Here, it's empty. And now, so this goes along and it creates, so I mean, the net infra configuration here, this is the CFS, right? Now if you look at devices, we'll actually have, so the devices themselves inside of NSO, those are created based on the CFS input. And of course, as you know, if you add a device into NSO, there's a whole little couple of steps you got to take, you got to sync from and stuff like this, right? So we have automation logic in here, a package called device automaton, but then we also have other services that react and work together with this package. And maybe this is the, so I should of course have logged into this device before I started as well, right? But you'll have to take my word for it. This is one of those routers, right? So I'm running CRPD. It's the Juniper's containerized thingy. So it's much more lightweight. I have like a very old laptop, so I can't run one of these virtual routers. But running these 6 or 9 of them on this laptop works beautifully. And it's kind of cool because we got a control plane, right? So I mean, that configuration, very abstract, you know, it actually boils down to device configuration, and we get a running network. How out of time are we? I'll just show some of this stuff, right? So you get the idea. If we drop down here to the sort of RFS layer, we have this nodes layer that we call. This is essentially RFS. We can see how it's organized exactly by device that I showed you, right? So we have a router, CR1 here. We have certain configuration parameters that pertain or relate to the base configuration. And then we have these backbone interfaces. So all these are our RFS services. And at this point, we have all of this detailed information, right? So we like to build services like that once we reach RFS, they're very simple. We don't do resource allocation in the RFS. We want to do that up sort of front earlier, right? And then when we're down here, we all have sort of concrete, detailed data. And yeah, so there's a bunch of backbone interfaces, and then there are IBGP neighbor services like this, right? And those are constructed. We can look at the this is the intermediate layer. In the slides, it's called intermediate, right? Here we call it infra-internal. Here we have the IBGP full mesh. It's a very small one in this case. We just have three of these core routers, right? But that's where we add these in. And for example, if we want to look at, you know, where did these come from? You can look at the service metadata and see that, oh, okay, yeah, you know, this one, who wrote this data over here? Well, it's this one, right? Net infra and then CR3, right? And that was that very top show configuration. These are the very top CFS layers.
I think we have to end there.
Yeah, excellent. I was about to say, I think we'll stop the demo right
Any
there.
questions? Do you have
No time for questions.
no time
I
for
think.
questions?
But we'll be outside.
Find us.
Yes.
Yeah.
Yes. Just talk to us.
But before you leave, we're continuing tomorrow.
Same
right?
time, same place.
Same time, same place, and with more demo and
Yes.
more time, I hope.
Thank you.